tides of the rise and fall of sea levels caused by the combined effects of the gravitational forces exerted by the Moon and the Sun and the rotation of the Earth. The times and amplitude of tides at a locale are influenced by the alignment of the Sun and Moon, by the pattern of tides in the deep ocean, by the amphidromic systems of the oceans, and the shape of the coastline and near-shore bathymetry. Some shorelines experience a semi-diurnal tide, two nearly equal high and low tides each day. Other locations experience a diurnal tide, only one high and low tide each day. A mixed tide, two uneven tides a day, or one high and one low, is also possible. Tides vary on timescales ranging from hours to years due to a number of factors. To make accurate records, tide gauges at fixed stations measure the water level over time. Gauges ignore variations caused by waves with periods shorter than minutes. These data are compared to the reference level, usually called mean sea level. While tides are usually the largest source of short-term sea level fluctuations, sea levels are also subject to forces such as wind and barometric pressure changes, resulting in storm surges, especially in shallow seas and near coasts. Tidal phenomena are not limited to the oceans, but can occur in other systems whenever a gravitational field that varies in time and space is present. For example, the solid part of the Earth is affected by tides, though this is not as easily seen as the water tidal movements. Characteristics. Tide changes proceed via the following stages. Sea level rises over several hours, covering the intertidal zone, flood tide. The water rises to its highest level, reaching high tide. Sea level falls over several hours, revealing the intertidal zone, ebb tide. The water stops falling, reaching low tide. Tides produce oscillating currents known as tidal streams. The moment that the tidal current ceases is called slack water, a slack tide. The tide then reverses direction and is said to be turning. Slack water usually occurs near high water and low water, but there are locations where the moments of slack tide differ significantly from those of high and low water. Tides are commonly semi-diurnal or diurnal. The two high waters on a given day are typically not the same height. These are the higher high water and the lower high water in tide tables. Similarly, the two low waters each day are the higher low water and the low water. The daily inequality is not consistent and is generally small when the Moon is over the equator. Tidal constituents. Tidal constituents are the net result of multiple influences impacting tidal changes over certain periods of time. Primary constituents include the Earth's rotation, the position of the Moon and Sun relative to the Earth, the Moon's altitude above the Earth's equator, and bathymetry. Variations with periods of less than half a day are called harmonic constituents. Conversely, cycles of days, months, or years are referred to as long-period constituents. The tidal forces affect the entire Earth, but the movement of the solid Earth is only centimeters. The atmosphere is much more fluid and compressible, so its surface moves kilometers. In the sense of the contour level of a particular low pressure in the outer atmosphere. Principal lunar semi-diurnal constituent. In most locations, the largest constituent is the principal lunar semi-diurnal, also known as the M2 tidal constituent. Its period is about 12 hours and 25.2 minutes, exactly half a tidal lunar day, which is the average time separating one lunar zenith from the next, and thus is the time required for the Earth to rotate once relative to the Moon. Simple tide clocks track this constituent. The lunar day is longer than the Earth day because the Moon orbits in the same direction the Earth spins. This is analogous to the minute hand on a watch crossing the hour hand at 12 o'clock and then again at about 1:05 1/2. The Moon orbits the Earth in the same direction as the Earth rotates on its axis. so it takes slightly more than a day, about 24 hours and 50 minutes, for the Moon to return to the same location in the sky. During this time, it has passed overhead once and underfoot once, so in many places the period of strongest tidal forcing is the above-mentioned, about 12 hours and 25 minutes. The moment of highest tide is not necessarily when the Moon is nearest to zenith or nadir, but the period of the forcing still determines the time between high tides, because the gravitational field created by the Moon weakens with distance from the Moon. It exerts a slightly stronger than average force on the side of the Earth facing the Moon, and a slightly weaker force on the opposite side. The Moon thus tends to stretch the Earth slightly along the line connecting the two bodies. The solid Earth deforms a bit, but ocean water, being fluid, is free to move much more in response to the tidal force, particularly horizontally. As the Earth rotates, the magnitude and direction of the tidal force at any particular point on the Earth's surface change constantly. Although the ocean never reaches equilibrium, there is never time for the fluid to catch up to the state it would eventually reach if the tidal force were constant. The changing tidal force nonetheless causes rhythmic changes in sea surface height. Semi-diurnal range differences. When there are two high tides each day with different heights, the pattern is called a mixed semi-diurnal tide. Range variation. Springs and neaps. The semi-diurnal range varies in a 2-week cycle, approximately twice a month, around new moon and full moon when the Sun, Moon, and Earth form a line. The tidal force due to the Sun reinforces that due to the Moon. The tide's range is then at its maximum. This is called the spring tide. It is not named after the season, but, like that word, derives from the meaning jump, burst forth, rise, as in a natural spring. When the Moon is at first quarter or third quarter, the Sun and Moon are separated by 90 degrees when viewed from the Earth, and the solar tidal force partially cancels the Moon's. At these points in the lunar cycle, the tide's range is at its minimum. This is called the neap tide, or neaps. Neap is an Anglo-Saxon word meaning without the power, as in Ford Gange's nip. Spring tides result in high waters that are higher than average, low waters that are lower than average, slack water time that is shorter than average, and stronger tidal currents than average. Neaps result in less extreme tidal conditions. There is about a 7-day interval between springs and neaps. Lunar altitude. The changing distance separating the Moon and Earth also affects tide heights. When the Moon is closest, at perigee, the range increases, and when it is at apogee, the range shrinks. Every 7.5 lunations, perigee coincides with either a new or full moon, causing perigee and spring tides with the largest tidal range. Even at its most powerful, this force is still weak, causing tidal differences of inches at most. Bathymetry. The shape of the shoreline and the ocean floor changes the way that tides propagate, so there is no simple, general rule that predicts the time of high water from the Moon's position in the sky. Coastal characteristics such as underwater bathymetry and coastline shape mean that individual location characteristics affect tide forecasting. Actual high water time and height may differ from model predictions due to the coastal morphology's effects on tidal flow. However, for a given location, the relationship between lunar altitude and the time of high or low tide is relatively constant and predictable, as is the time of high or low tide relative to other points on the same coast. For example, the high tide at Norfolk, Virginia, U.S. predictably occurs approximately 2.5 hours before the Moon passes directly overhead. Land masses and ocean basins act as barriers against water moving freely around the globe, and the varied shapes and sizes affect the size of tidal frequencies. As a result, tidal patterns vary. For example, in the The east coast has predominantly semi-diurnal tides, as do Europe's Atlantic coasts, while the west coast predominantly has mixed tides. Other constituents. These include solar gravitational effects, the obliquity of the Earth's equator and rotational axis, the inclination of the plane of the lunar orbit and the elliptical shape of the Earth's orbit of the Sun. A compound tide results from the shallow water interaction of its two parent waves, phase and amplitude. Because the M2 tidal constituent dominates in most locations, the stage or phase of a tide, denoted by the time in hours after high water, is a useful concept. Tidal stage is also measured in degrees, with 360 degrees per tidal cycle. Lines of constant tidal phase are called cotidal lines, which are analogous to contour lines of constant altitude on topographical maps. High water is reached simultaneously along the cotidal lines extending from the coast out into the ocean, and cotidal lines advance along the coast. Semi-diurnal and long phase constituents are measured from high water, diurnal from maximum flood tide. This and the discussion that follows is precisely true only for a single tidal constituent. For an ocean in the shape of a circular basin enclosed by a coastline, the cotidal lines point radially inward and must eventually meet at a common point, the amphidromic point. The amphidromic point is at once cotidal with high and low waters, which is satisfied by zero tidal motion. Tidal motion generally lessens moving away from continental coasts, so that crossing the cotidal lines are contours of constant amplitude which decrease to zero at the amphidromic point. For a semi-diurnal tide, the amphidromic point can be thought of roughly like the center of a clock face, with the hour hand pointing in the direction of the high water cotidal line, which is directly opposite the low water cotidal line. High water rotates about the amphidromic point once every 12 hours in the direction of rising cotidal lines, and away from ebbing cotidal lines. This rotation is generally clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, and is caused by the Coriolis effect. The difference of cotidal phase from the phase of a reference tide is the epoch. The reference tide is the hypothetical constituent equilibrium tide on a landless Earth measured at 0 degrees longitude, the Greenwich meridian, in the North Atlantic, because the cotidal lines circulate counterclockwise around the amphidromic point. The high tide passes New York Harbor approximately an hour ahead of Norfolk Harbor. South of Cape Hatteras, the tidal forces are more complex and cannot be predicted reliably based on the North Atlantic cotidal lines. Physics. History of tidal physics. Investigation into tidal physics was important in the early development of heliocentrism and celestial mechanics, with the existence of two daily tides being explained by the Moon's gravity. Later, the daily tides were explained more precisely by the interaction of the Moon's and the Sun's gravity. Seleucus of Seleucia theorized around 150 BC that tides were caused by the Moon. Medieval understanding of the tides was primarily based on works of Muslim astronomers, which became available through Latin translations starting from the 12th century. Abu Mazhar, in his Introductorium in Astronomium, taught that ebb and flood tides were caused by the Moon, also reckoned that the Moon is involved. Abu Mazhar discussed the effects of wind and Moon's phases relative to the Sun on the tides. In the 12th century, al-Batruji contributed the notion that the tides were caused by the general circulation of the heavens. Simon Stevan, in his 1608 Der Spiegelung der Ebenflüsse, The Theory of Ebb and Flood, dismissed a large number of misconceptions that still existed about ebb and flood. Stevan pleaded for the idea that the attraction of the Moon was responsible for the tides and spoke in clear terms about ebb, flood, spring tide and neap tide, stressing that further research needed to be made. In 1609, Johannes Kepler also correctly suggested that the gravitation of the Moon caused the tides, which he based upon ancient observations and correlations. It was originally mentioned in Ptolemy's Tetrabiblos as having derived from ancient observation. Galileo Galilei, in his 1632 dialogue concerning the two chief world systems, whose working title was Dialogue on the Tides, gave an explanation of the tides. The resulting theory, however, was incorrect, as he attributed the tides to the sloshing of water caused by the Earth's movement around the Sun. He hoped to provide mechanical proof of the Earth's movement. The value of his tidal theory is disputed. Galileo rejected Kepler's explanation of the tides. Isaac Newton was the first person to explain tides as the product of the gravitational attraction of astronomical masses. His explanation of the tides was published in the Principia and used his theory of universal gravitation to explain the lunar and solar attractions as the origin of the tide-generating forces. Newton and others before Pierre-Simon Laplace worked the problem from the perspective of a static system that provided an approximation that described the tides that would occur in a non-inertial ocean evenly covering the whole Earth. The tide-generating force is still relevant to tidal theory, but as an intermediate quantity rather than as a final result. Theory must also consider the Earth's accumulated dynamic tidal response to the applied forces, which response is influenced by ocean depth, the Earth's rotation, and other factors. In 1740, the Académie Royale des Sciences in Paris offered a prize for the best theoretical essay on tides. Daniel Bernoulli, Leonhard Euler, Colin Maclaurin and Antoine Cavalieri shared the prize. Maclaurin used Newton's theory to show that a smooth sphere covered by sufficiently deep ocean under the tidal force of a single deforming body is a prolate spheroid with major axis directed toward the deforming body. Maclaurin was the first to write about the Earth's rotational effects on motion. Euler realized that the tidal force's horizontal component drives the tide. In 1744, Jean-Laurent d'Alembert studied tidal equations for the atmosphere which did not include rotation. In 1770, James Cook's bark HMS Endeavour grounded on the Great Barrier Reef. Attempts were made to refloat her on the following tide which failed, but the tide after that lifted her clear with ease. Whilst she was being repaired in the mouth of the Endeavour River, Cook observed the tides over a period of 7 weeks. At neap tides both tides in a day were similar, but at springs the tides rose 7 feet in the morning but 9 feet in the evening. Pierre-Simon Laplace formulated a system of partial differential equations relating the ocean's horizontal flow to its surface height, the first major dynamic theory for water tides. The Laplace tidal equations are still in use today. William Thomson, 1st Baron Kelvin, rewrote Laplace's equations in terms of vorticity, which allowed for solutions describing tidally driven coastally trapped waves, known as Kelvin waves. Others, including Kelvin and Henri Poincaré, further developed Laplace's theory. Based on these developments and the lunar theory of E.W. Brown describing the motions of the Moon, Arthur Thomas Doodson developed and published in 1921 the first modern development of the tide-generating potential in harmonic form. Doodson distinguished 388 tidal frequencies. Some of his methods remain in use. Forces. The tidal force produced by a massive object on a small particle located on or in an extensive body is the vector difference between the gravitational force exerted by the Moon on the particle, and the gravitational force that would be exerted on the particle if it were located at the Earth's center of mass. The solar gravitational force on the Earth is on average 179 times stronger than the lunar. but because the Sun is on average 389 times farther from the Earth, its field gradient is weaker. The solar tidal force is 46% as large as the lunar. More precisely, the lunar tidal acceleration is about 1.1 times 10⁻⁷ grams, while the solar tidal acceleration is about 0.52 times 10⁻⁷ grams, where g is the gravitational acceleration at the Earth's surface. Venus has the largest effect of the other planets, at 0.000113 times the solar effect. The ocean's surface is closely approximated by an equipotential surface, commonly referred to as the geoid. Since the gravitational force is equal to the potential's gradient, there are no tangential forces on such a surface, and the ocean's surface is thus in gravitational equilibrium. Now consider the effect of massive external bodies such as the Moon and Sun. These bodies have strong gravitational fields that diminish with distance and act to alter the shape of an equipotential surface on the Earth. This deformation has a fixed spatial orientation relative to the influencing body. The Earth's rotation relative to this shape causes the daily tidal cycle. Gravitational forces follow an inverse square law, but tidal forces are inversely proportional to the cube of the distance. The ocean surface moves because of the changing tidal equipotential, rising when the tidal potential is high, which occurs on the parts of the Earth nearest to and furthest from the Moon. When the tidal equipotential changes, the ocean surface is no longer aligned with it, so the apparent direction of the vertical shifts. The surface then experiences a downslope in the direction that the equipotential has risen. Laplace's tidal equations, ocean depth so much smaller than the horizontal extent. Thus, the response to tidal forcing can be modeled using the Laplace tidal equations, which incorporate the following features. The vertical velocity is negligible, and there is no vertical shear. This is a sheet flow. The forcing is only horizontal. The Coriolis effect appears as an inertial force acting laterally to the direction of flow and proportional to velocity. The surface height's rate of change is proportional to the negative divergence of velocity multiplied by the depth. As the horizontal velocity stretches or compresses the ocean as a sheet, the volume thins or thickens, respectively. The boundary conditions dictate no flow across the coastline and free slip at the bottom. The Coriolis effect steers flows moving towards the equator to the west and flows moving away from the equator toward the east, allowing coastally trapped waves. Finally, a dissipation term can be added, which is an analog to viscosity, amplitude and cycle time. The theoretical amplitude of oceanic tides caused by the Moon is about 54 centimeters at the highest point, which corresponds to the amplitude that would be reached if the ocean possessed a uniform depth, there were no land masses, and the Earth were rotating in step with the Moon's orbit. The Sun similarly causes tides, of which the theoretical amplitude is about 25 centimeters with a cycle time of 12 hours. At spring tide, the two effects add to each other to a theoretical level of 79 centimeters, while at neap tide the theoretical level is reduced to 29 centimeters. Since the orbits of the Earth about the Sun, and the Moon about the Earth, are elliptical, tidal amplitudes change somewhat as a result of the varying Earth-Sun and Earth-Moon distances. This causes a variation in the tidal force and theoretical amplitude of about plus or minus 18% for the Moon and plus or minus 5% for the Sun. If both the Sun and Moon were at their closest positions and aligned at new moon, the theoretical amplitude would reach 93 centimeters. Real amplitudes differ considerably, not only because of depth variations and continental obstacles, but also because wave propagation across the ocean has a natural period of the same order of magnitude as the rotation period. If there were no land masses, it would take take about 30 hours for a long wavelength surface wave to propagate along the equator halfway around the Earth. Earth tides, which raise and lower the bottom of the ocean, and the tide zone gravitational self-attraction are both significant and further complicate the ocean's response to tidal forces. Dissipation. Earth's tidal oscillations introduce dissipation at an average rate of about 3.75 terawatts. About 98% of this dissipation is by marine tidal movement. Dissipation arises as basin-scale tidal flows drive smaller-scale flows which experience turbulent dissipation. This tidal drag creates torque on the Moon that gradually transfers angular momentum to its orbit, and a gradual increase in Earth-Moon separation. The equal and opposite torque on the Earth correspondingly decreases its rotational velocity. Thus, over geologic time, the Moon recedes from the Earth at about 3.8 centimeters per year, lengthening the terrestrial day. Day length has increased by about 2 hours in the last 600 million years. Assuming that the deceleration rate has been constant, this would imply that 70 million years ago, day length was on the order of 1% shorter, with about 4 more days per year. Navigation. Tidal flows are important for navigation, and significant errors in position occur if they are not accommodated. Tidal heights are also important. For example, many rivers and harbors have a shallow bar at the entrance which prevents boats with significant draft from entering at low tide. Until the advent of automated navigation, competence in calculating tidal effects was important to naval officers. The certificate of examination for lieutenants in the Royal Navy once declared that the prospective officer was able to shift his tides. Tidal flow timings and velocities appear in tide charts or a tidal stream atlas. Tide charts come in sets. Each chart covers a single hour between one high water and another and show the average tidal flow for that hour. An arrow on the tidal chart indicates the direction and the average flow speed for spring and neap tides. If a tide chart is not available, most nautical charts have tidal diamonds, which relate specific points on the chart to a table giving tidal flow direction and speed. The standard procedure to counteract tidal effects on navigation is to calculate a dead reckoning position from travel distance and direction. Mark the chart and draw a line from the doctor in the tide's direction. The distance the tide moves the boat along this line is computed by the tidal speed, and this gives an estimated position, or EP. Nautical charts display the water's charted depth at specific locations with soundings, and the use of bathymetric contour lines to depict the submerged surface's shape. These depths are relative to a chart datum, which is typically the water level at the lowest possible astronomical tide and therefore the minimum possible water depth during the tidal cycle. Drying heights may also be shown on the chart, which are the heights of the exposed seabed at the lowest astronomical tide. Tide tables list each day's high and low water heights and times. To calculate the actual water depth, add the charted depth to the published tide height. Depth for other times can be derived from tidal curves published for major ports. The rule of twelfths can suffice if an accurate curve is not available. This approximation presumes that the increase in depth in the 6 hours between low and high water is: first hour 1/12, second 2/12, third 3/12, fourth 3/12, fifth 2/12, sixth 1/12.